Dear all, welcome to the wastewater treatment model, which is integrated in the wastewater management decision support tool for Drin River Basin. Wastewater management decision support tool, WEMDST, contains a hydraulic model, agglomeration load model, wastewater treatment model, and water quality model. This video is for the presentation of the wastewater treatment model. The idea behind WEMDST is to identify which agglomerations should be equipped with wastewater treatment plants first in order to maximize the effect on river bodies. The wastewater treatment model is composed of treatment and economic model and will be presented on the next slides. The wastewater treatment model is developed for the initial stage of addressing wastewater issues. The decisions made can significantly impact the project's economic and environmental performance. Thus, it's imperative to incorporate sustainability considerations early in the process. The wastewater treatment model will give us answers about treatment efficiency and related emission control costs to achieve required effluent standards. The treatment model is based on discharge requirements set in the Urban Wastewater Directive. Secondary treatment is obligatory for agglomerations above 2,000 population equivalents, and tertiary treatment or advanced treatment is obligatory for agglomerations above 10,000 population equivalents in designated sensitive areas and their catchments. So these are two criteria giving us the effluent requirements for the model on which the treatment process is based on. In addition, the model takes into account requirements for sludge and wastewater reuse. Other input data we used are hydraulic and pollution loadings for the design of wastewater treatment plants. We used theoretical values relevant for Drin region. For hydraulic loadings, we used a specific water consumption rate of 120 liters per PE per day. And for the influent load, we used relevant standards. All this data was required to design a technology model of wastewater treatment plants adapted to the Drin region. The treatment model is based on most commonly used wastewater technologies. That are technologies such as sequential batch reactor, classic wastewater treatment plant, trickling filters, and so on, which are all using activated sludge to achieve the required level of treatment. The biological processes are only dependent on the concentration in a reactor at the place where the conversion takes place. This part of a process model is therefore universal and can be formulated as a general activated sludge model. An increase in treatment complexity would not increase the quality of the developed model. We will present first the treatment model. The model is divided in treatment model and sludge model. The treatment model can simulate secondary and tertiary treatment, and sludge model uses produced data. Sludge management issues are too often neglected, and that is why sludge treatment is addressed separately. The user can choose between two technological options for sludge treatment: mechanical dewatering and sludge drying reed beds. Mechanical dewatering is done mechanically using belt presses or centrifuges, for example, and sludge drying reed beds are a nature-based solution enabling sludge reuse. Modeling can also give us some indicative values regarding wastewater reuse and sludge reuse. It estimates cost, quantities, and needed agriculture area. German design guidelines have been followed for the sizing of wastewater treatment plant model. The basis for facility sizing is presented in the table. Model does not include primary clarifiers because anaerobic sludge stabilization is not included in the sludge treatment line. However, this kind of sludge treatment can be of interest for wastewater treatment plants with capacity bigger than 100,000 PE. For secondary treatment level, model predicts anaerobic selector plus nitrification aeration tank. And for tertiary treatment level, model predicts anaerobic selector plus nitrification plus denitrification aeration tank. With the use of sludge treatment model, the user can compare mechanical dewatering versus sludge drying reed beds. Reed beds can achieve higher solid content, up to 40%, while mechanical dewatering usually achieves around 20% of dry matter. The percentages used in the model for mechanical dewatering are 20% of dry matter for secondary treatment and 22% of dry matter for tertiary treatment. Mechanical treatment processes use coagulants or flocculants for sludge thickening and dewatering, while sludge drying reed beds are based on natural processes involving filtration, evapotranspiration, and plant uptake. Sludge drying reed beds can also achieve lower organic content due to mineralization, but require a much larger area compared to mechanical dewatering. Sludge drying reed beds are a passive technology with low energy input, and mechanical dewatering is an intensive technology. The goal of sludge treatment is to reduce sludge volume and make sludge handling easier and cheaper. Smaller amount of sludge at the end of the process reduces overall disposal costs. Anyone from the wastewater sector is aware that since mechanical dewatering emerged, it has been widely used. Co-natural technologies like sludge drying reed beds are less known to decision makers, and consequently also less used. Sludge drying reed beds can treat primary and secondary sludge as well as their mixtures. The solid fraction of the sludge remains on the surface, while water drains out of the system through the filter media. The critical improvement of the planted bed over the unplanted bed is that the filters do not need to be dislodged after each feeding drying cycle. Fresh sludge can be directly applied to the previous layer. The plants and their root systems maintain the filter's porosity. It is expected that the reed beds can be in operation for more than 30 years. After approximately 8 to 10 years of operation, beds are emptied sequentially. Pathogen die-off is assured by applying resting period of 4 to 6 months. The final product from the reed bed is dewatered, mineralized, and stabilized sludge. It is an earthy material, compost-like, which can be reduced according to the national standards. On the first picture, you can see how sludge drying reed beds look like. These green beds next to the wastewater treatment plant. It is an example from Mojkovac in Montenegro. The sludge drying reed beds were built in 2016 to minimize high operational costs of mechanical dewatering. Here I would like to emphasize how important it is to strategically address sludge management already in the phase of wastewater treatment planning. We could all learn from our experience in Slovenia. We have found ourselves in the middle of an ecological crisis due to the Hungarian ban on imports of foreign sludge. For years, municipalities have chosen the cheapest sludge disposal option, that was exports to Hungary, and therefore they were not open to any other suggestions or innovations. The price of sludge disposal went overnight from €60 per ton to more than €200 per ton. One of the key advantages of adopting circular economy principles in the processing of wastewater is that resource recovery and reuse can transform sanitation from a costly service to one that is self-sustaining and adds value to the economy. The model calculates how much sludge per year is being produced in wastewater treatment plant. This data is then used to estimate costs for sludge final disposal. Reclaimed wastewater can provide a reliable alternative water supply for agricultural irrigation or other uses. In order to reuse wastewater, we have to remove pathogens, and this is commonly done by ultraviolet radiation. Reuse model uses wastewater treatment plant hydraulic parameters and discharge requirements. Proper capacity of UV system is based on 3 variables: maximum flow, dose required, and UV transmittance of the water. The technology used in the model enables 3-log reduction of pathogens after the biological treatment. Introduction into the wastewater technology model was needed in order to understand concept behind the model and what are the basis for cost analysis. Now we will present the economic model. Model estimates capital and operational costs. Cost functions are based on experiences with wastewater treatment plants design over many years and actual cost of past projects in the Western Balkan region. Developed concept covers important aspects of life cycle cost analysis. It addresses the planning, design, construction, operation, and decommissioning of wastewater treatment plant. Cost functions are available for all technologies presented in the previous slides. Here you can see what kind of cost categories the model takes into account. CAPEX covers design and construction, and OPEX covers categories such as energy, reagents, workforce, maintenance, and monitoring. The use prices in the model are presented in this gray box. Capital expenditures, or CAPEX, are related to investments in assets that will last for many years. CAPEX functions for secondary and tertiary wastewater treatment are on the left. The investment in wastewater treatment plant for secondary treatment is for around 11% cheaper than the investment in the wastewater treatment plant for tertiary treatment. The CAPEX expressed in euro per PE decreases by agglomeration size. That means that small wastewater treatment plant represents a higher financial burden per inhabitant. The same applies for sludge treatment. And investment costs in reed beds are much higher than investment costs in mechanical dewatering. The sludge treatment costs are also higher for secondary treatment because the treatment process produces more sludge. On this slide are presented CAPEX costs for wastewater disinfection and sewage system. Wastewater disinfection is cheaper for tertiary treatment because water is already more purified, more transparent, and less land power is required. Model also provides indicative CAPEX costs for the sewage system, but these values should be used with great care. The meter of sewage system costs on average around 200 euro per meter, but the price depends on the depth, material, number of pumping stations, population density, and so on. And now let's take a look at operational costs. Operational expenditures include expenses required to operate and maintain the wastewater system assets. On the left, we can see operational cost of wastewater treatment, and on the right, operational cost of sludge treatment. Operational costs for wastewater treatment plants represent around 5% of the CAPEX without sludge handling, which is presented separately on your right. We can see that OPEX for wastewater treatment is for wastewater treatment plant with capacity 2000 PE, between 60 and 64 euro per PE, and it decreases with agglomeration size. So for the wastewater treatment plant with capacity 200,000 PE is from 25 to 27 euro per PE. Wastewater treatment plant for 200,000 PE for tertiary level of treatment has also around 20% bigger OPEX compared to wastewater treatment plant for secondary level of treatment. And regarding sludge operational costs, they're highest for mechanical dewatering with incineration, while lowest are operational costs of sludge drying reed beds with local sludge reuse. Although investment costs in reed beds are higher, the operational costs are much lower, and experience shows that investment in reed bed can return in 7 to 10 years through the cost savings. We use 60 euro per ton for sludge incineration and 15 euros per ton for local reuse. The operational expenditures for wastewater reuse cover energy, UV lamps, maintenance, and other spare parts. The operational costs for wastewater treatment plant for tertiary treatment are lower than the operational costs for wastewater treatment plant with secondary treatment. Cost analysis model also includes net present value, which is an indicator for overall project performance and is used for ranking the options from financial point of view. The average economic life of the project assets is assumed to be 30 years. The real discount rate applied is 4%. Cash inflows, such as revenues from water tariffs, are not included in the calculation. So comparing total net present value, including investment and operational costs for wastewater treatment plants with capacity 100,000 PE, show that reed beds with sludge reuse are the better option in the long term. Land acquisition costs are not part of the model and are not included in the investment costs. The cost of the land may vary greatly depending on its use, productivity, potential alternative uses, availability. So the generalization for Drin catchment is not applicable within the scope of this project. However, land costs are highly relevant to the entire investment and should be included in cost analysis. Given that sludge drying reed beds require a large land area, much bigger than mechanical dewatering, model contains indicative values for required filter area, that is without embankments and maintenance roads. What are the conclusions? The wastewater treatment model supports technological and financial wastewater planning process. So, as we have seen, it can estimate the investment and operational costs and also net present value, also sludge reuse and wastewater reuse. But at the same time, the tool itself is not enough for successful project preparation. We have to be aware that it takes much more to address all the critical issues of wastewater treatment planning. Here we listed only a few questions local authorities should seek answers to. To conclude, wastewater treatment planning is a complex process and every location and therefore every wastewater treatment plant is site-specific.